This is Self-Directed Research. Our hosts, James and Amos, get hyped about different topics and take turns each week presenting their ideas to each other. You can check out the website, YouTube, or Spotify to watch this episode's presentation, and visit sdr-podcast.com/episodes for previous episodes with presentations, videos, show notes, and transcripts. New episodes are published every Wednesday. This episode is brought to you by CodeCrafters. There's more info at the end of the episode, or check out the link in our show notes to try it out for free. If you upgrade your plan, it supports this podcast. The costs can often be covered or reimbursed by your company, so it's worth asking about. Amos is up this week, exceeding the arbitrary time limit with 45 slides covering the topic target triples. Hope you enjoy.
All I remember, James, were you alive when, probably, people were passing around an ASCII art version of the Star Wars movie? Like, you had to right-size the notepad window, and then you could hit page down, just like hold it, and then the repeat would make like a flipbook, but in notepad for Windows 95. All right, I'm gonna share my screen. Is everybody ready?
No.
No?
Yes.
Yes.
Yeah.
You know, the fun thing is that every time I move my lips, it hurts because the interior of my lips rubs against very sharp metal bits, and so I've started correcting by just mumbling instead of pronouncing words because it hurts less. I'm optimizing for least pain. When we record the podcast or when I record a video, I need to consciously reverse that and make it hurt so that it sounds good. It's fun. I love it.
I did 3 or 4 years of braces too. So, I mean,
Yeah.
I have not recently felt your pain, but I've absolutely felt your pain in the past. To be fair, I didn't have a podcast when I was in 6th grade. So
maybe you should have, James.
That was a blessing, I guess. It was a blessing for both me and the world, I think. But
What would it have been about in 6th grade?
I don't know. What was I into? Probably video games or Pokemon at that point.
Oh, yeah. Mine would have probably been like Spyro and Crash Bandicoot.
Spyro? Sign me up.
Mine would have been like N64 games and
yeah.
Pokemon and anime, maybe, like Dragon Ball Z and stuff like that.
Okay. Well, unfortunately, today's podcast is about target triples. I have a subtitle here because I'm contractually obligated to come up with subtitles for this podcast against my will.
Thank you.
And subtitle is Lies, Damn Lies, and Target Triples, which repeats the title. I don't know if that's legal. I have no idea.
I accept it. It's fine.
Thanks, Amanda. What's a target? It's machine that code can run on. James, you have 15 seconds to disagree.
It's more specific than that because
It
one
is.
machine can have different operating systems, ABIs, configurations.
Yeah, we're
Yeah.
getting to that, as you can imagine. It's called a target triple, which has the prefix try, so you would expect it to have 3 components. If you do check the target triple on the machine that I'm recording this from, which is a Mac Studio, if you do rusty-v capital V, like lowercase v capital V, which stands for verbose version, then you get the full version of Rusty, which includes 182.0, that's the current stable. You get the commit hash, the commit date, and the host shows arch64-apple-darwin. So we're going to get into what each of those components mean. So when arch64 Apple Darwin, arch64 is the architecture. In that case, it means 64-bit ARM. We'll get into ARM naming conventions. I have 45 slides. Get ready. The second segment in this case is the vendor. It's Apple. And the last segment in this case is the operating system, which is Darwin. Funny, I don't remember installing Darwin on this computer. Darwin is the name that Steve Jobs came up when he was interim CEO of Apple in 1999 because, and I quote, "It's about evolution." I'm very glad that I found the slide. Again, if you're not looking at slides, you're missing out. You can go to sdr-podcast.com to find the episode and find the slides for this. It's an article from Wired that says Apple opens OS code.
I'd like to interject for a second. What you've been referring to as Mac OS X is actually Mac OS X running on the Darwin kernel, or as I like to call it, Mac OS X plus Darwin.
Well, okay.
Can I be an Apple neckbeard?
You can. I started looking into this. There's the whole history, like the lineage of like BSD and Next Step and Open Step, and Darwin was supposed to be this open thing where like they said, we believe that putting it out there will help us make it the best technology collectively we know how to make. So it was Apple saying, oh, we're open now. Everybody can come contribute. Nowadays, it's like, yeah, they have an FTP server essentially that are legally required to have where they dump source code and you can look at it, I guess.
I'm just here so I won't get fined.
That's exactly it. So there's a whole history there, which would make a fascinating other episode, because this is only slide 8. So I had to cut the research short. People will write emails about this. It is fine. I accept the responsibility on behalf of our producer, Amanda, who will actually have to look at those. So there's other targets that look like it. Mine is AR64 Apple Darwin, but there's also x86_64-Apple-Darwin. I'm going to be saying a lot of punctuation out loud, so get used to it. Those were Intel Macs. Those we had before the Apple Silicon Macs. So Apple M1, M2, M3, M4, those are Apple Silicon, they're AR64. But before that, we had Intel Macs. I still have one of them, and you can recognize them very easily. The fan makes a noise when they turn on.
They are loud and hot.
Yes, like me.
Yeah, I was going to say, I was looking around. I have one in my house, but not in this room.
Before Intel Macs, we had PowerPC Macs. James just is making big eyes at my slide with a picture of
Hell yeah, 68K Max.
a Mac Quadra 605. I don't actually know what it is.
Oh, sorry, no, this is PowerPC.
Yeah.
68K is before that.
Yeah. Oh, we'll get to 68K. Don't you worry.
I don't actually know what it is from the web.
Siri just woke up for some reason. I talked about the Quadra 605, and Siri was like, I will help.
Friend.
Rust-C, the Rust compiler, has a bunch of PowerPC targets. There's 3 levels of support, which we'll get into roughly what they mean. There's 3 PowerPC tier 2 targets in Rust. PowerPC-unknown-linux-GNU, PowerPC 64 the same thing, and PowerPC 64 LE for Little Endian the same thing. What devices are still PowerPC today? Because those are actually maintained. I was trying to find the answer and I tweeted about it. You might have seen it and answered something useful. Why is PowerPC still relevant today? A couple of answers. As recently as the PS3, the Sony PlayStation 3 console, they were using PowerPC-based processors on there. PS4 and PS5 changed.
That was the Cell processor. Was the Cell PowerPC
Yes.
based? Because Cell was its own weird
It is.
architecture that only the PS3 used.
I have speaker notes. I come prepared this time. The PS3 uses
Nice.
the Cell microprocessor, which is made up of one 3.2 gigahertz PowerPC-based power processing element and 6 accessible synergistic processing elements, SPEs. So yes, it is, at least part of it is PowerPC-based. And then also, Apple used to make servers. Remember that? They made the Xserve G5. I think that's the last one they released. We have a picture of it here with typical Apple marketing, which means there's nice shadows and like little reflections on the image. It says, more power, less energy, introducing the fastest, most energy-efficient Xserve ever. It has several configurations that come in single processor, dual processor, cluster node, and they're like roughly between 2 and 2.3 gigahertz per processor.
Core, probably.
Yeah. It uses ECC memory with a 16 gigabytes maximum. I don't have the year here, which is a shame, but it is a server from another era for sure. But it was PowerPC. It still is. Some people are still running it, I imagine. IBM is probably the reason that PowerPC is still a tier 2 target in Rust-C, because they actually forked PowerPC in the 90s. I was born, butterfly flapped its wing, IBM forks PowerPC into an architecture called Power, which is not at all confusing, which is actually an acronym. It means performance optimization with enhanced risk. And by enhanced risk, they mean an instruction set that actually has 100 plus instructions and that supposedly has fixed width encoding, which is supposed to be a risk thing. But actually, they do have prefix instruction because they have a lot of SIMD stuff, like single instruction, multiple data. So Power is still used today as sort of a middle ground between like full-on mainframe and like smaller things. Some people still have Power hardware.
Do you know where else they are?
Banking?
A lot of radiation-hardened processors for satellites and Mars rovers and things like that are on CPUs like the RAD 750, which is a larger radiation-resistant PowerPC architecture designed to be resistant to the radiation you get in space or when there's not an atmosphere or a magnetosphere.
That's true.
They run slow, but they are generally qualified to be rad resistant.
Yeah.
They get used in either embedded systems, including goofy rad hardened embedded systems in space as well, still to this day.
Yeah, it's fun because like designing for satellites is completely different from designing for Earth because you have to worry about these. Raptor computing system came up when I asked people about PowerPC on social media. They make workstations you can buy starting at $9,977. So I ordered a couple just to get a feel for them.
Business expense.
Can we expense those, Amanda? Yes? Yeah. No. Okay. No, sorry. I'll just return them. It's fine. But they make new Power 9 workstations, even though IBM's already doing Power 10, because Power 9 was the last one. You could still, like, all the bits were free. So Power 10 is still up in the air for licensing reasons. There is Debian. The Debian Linux distribution makes a survey, a popularity contest, they call it, of which architecture are you running right now. And so we are looking, and you should be too. Go to sdr-podcast.com/episodes and find this episode. You can look at the slide that says number of submissions per architecture, and we can see, because it ranges from 2004 to 2024, so we got 20 years worth of like personal computing history in there and servers and whatnot. You can see the rise of 64-bit computing starting from 0 in 2004, going all the way to, well, it's just powers of 2, so it was like 262,000 respondents. And then you can see the slow decline of 32-bit, in this case, the i386 architecture. And you can see also the rise of ARM64. And then you cannot at all see PowerPC on there. The total responses for the last survey were 112 out of like a lot. I also got an actual response from someone who works on the Rust compiler. Why is PowerPC 64 tier 2? The simple answer is because there are people from IBM that care about fixing the target, and therefore it gets to be tier 2. Tier 2 requirements essentially boil down to, can we legally and without too much pain compile core and STD in RCI? And 2, are there people who we can call when it stops working? So that's all it takes to be a tier 2 target.
Yeah, there's 2 different flavors of tier 2. One is basically tier 2 hosted, which means that they can compile and run Cargo and Rust-C on it. And then there's ones particularly for the embedded system. So like all the embedded systems targets are all or mostly tier 2 because they are non-hosted ones. Because you can't run Cargo on a microcontroller, but you can compile to the microcontroller with Cargo.
Yes. There was an effort in July of 2023 to kind of sort out tier 2 targets because there were too many of them, and some of them didn't have documented maintainers. So it was like, oh, this one broke. Who do we call? We don't even know. It's not really clear. People changed jobs. They started documenting that better. The thing with tier 2 targets is that they can be either promoted to tier 1 or they can be demoted to tier 3. So there's a lot of different quality of targets in there. If we're looking at those PowerPC targets again, you may notice that for target triples, they have 4 components. There's PowerPC, which is the arch. There's unknown, which is the vendor. Linux is the operating system. And then GNU is the ABI.
Did you ever read the Hitchhiker's Guide to the Galaxies books?
I pretended I did, but I never actually.
That's fair. So they were writing the books, and they originally billed it as the Hitchhiker's Guide to the Galaxy trilogy, and then they made a 4th book, and on the title they said, the 4th entry in the increasingly less accurately named Hitchhiker's Guide to the Galaxy trilogy, or something like that. So this is exactly that experience again.
This is exactly it. The ones we're looking at ends with GNU for glibc, the GNU C library. But there's also Muzzle variants, which I say muzzle, some people say muscle, but it's actually spelled MUSL. And interestingly, the GNU target for x86_64-unknown-linux-GNU, that's the podcast you chose to listen, don't put the blame on us, is tier 1, but the Muzzle one is tier 2. And in most people's heads, the Muzzle target is there to serve as a fallback for when you download a binary that was linked against the glibc, but somehow your Linux distribution has a different version of glibc than their Linux distribution, so it doesn't actually run, and so you just get the Muzzle one instead, which is statically linked. We're looking at the slide that shows that the Muzzle build of Cargo Dist, for example, is statically linked. It doesn't have any dependency, so it should be able to run on any Linux system out there that supports LSB, I guess, but that's been a thing forever. Where was I going with this? Right, that people assume that the Muzzle target is statically linked, but actually it shouldn't be. And in 2021, the Rust compiler team accepted a major change that says, oh, right now we default Muzzle to be statically linked, but that was a mistake. And it turns out that there's people who actually care about dynamically linking against Muzzle, and those people are the people who develop Muzzle and Muzzle-based distributions like Alpine and Void Linux, and you can do that on Gentoo as well, I believe. And so, actually, we should change the default, which is going to break everyone else's assumptions of what the Muzzle target is for. I have like a zoomed-in part of the slide that just shows how you are now, after that change, supposed to actually enable static linking, and it's dash uppercase C targets dash feature equals plus CRT dash static. And the way you're supposed to disable it is to do equals dash CRT dash static or minus CRT dash static, I guess, in that sense. which is the most confusing naming scheme ever, and I hate it personally. But yeah, the change was approved in 2021. What happened since? It's really hard to actually make that change happen without making everyone instantly angry. And so I think that there's other like intermediate changes that they want to do first. But yeah, the real life is messy. We're roughly halfway through my slides, I would say. We're looking now at i686 PC Windows GNU. That's kind of a weird change. On the Debian graph earlier, we saw i386 as a placeholder for 32-bit processors, and this is chosen to be i686. Why? Because if you look at the history of Intel processors, you start in 1971 with the 4004, and then you have the 8008 in 72. Then you have the 8080, I'm going to call it, the 8-bit successor. Then you have the 8086, the first in the x86 series, like the 186, if we had a 186. And then they have the 286 and 82, which was 16-bit. And then the 386, which started the era of 32-bit processing. So that's why Debian calls it 386. It's because it is the first 32-bit processor in the Intel line, at least. I don't know about any other vendors. Then you have the 486, then you have the 586, which didn't actually get called 586, but it's like the Pentium. Then the 686 is the Pentium Pro, and then later the Pentium 2 and Pentium 3 also belong to that. And so actually in the Rust world, when you're looking at an i686 target, what you're talking about is it has streaming SIMD extensions. It has SSE support. So there's also i586 targets, which I don't know who uses, but it's 32-bit Linux without SSE, without those streaming SIMD extensions.
Yeah, I'm trying to think of another analog of this. It's sort of like, I know on Mac, it's basically setting like your enablement list of that of like, this is SDK version whatever and above, where like 386 means you only support the subset of features that does, where like 586 or 686 gets you a larger superset. Or it's also the reason why a lot of people, when they're compiling for high performance stuff, they do like native or whatever, because your processor is probably like, it's got a whole suite of things that the Rust compiler is not going to turn on because you told it like, pretend that I'm compiling for a machine from 2011 and not your wonderful machine in 2024 or whatever.
Yeah. But then if you do that, like you build something with March native and M2 native and whatnot, and then you deploy it to like a Hetzner server you got on the auction, and then it actually is a processor from like 2011, then you might notice SIG-IL, I think, just illegal instructions. Like, I don't have this extension. I don't have SSE 4.2, so no. So that's why this target is there.
There's like two really enthusiastic retro computer folks who are just very excited that they can run their... I think you can run Rust on like Windows 95 or Windows 98, and I think that's what that 586 target is for running it on like Windows 98.
Speaking of...
Oh, cool.
If you're making Windows binaries, I beg of you, please use the -MSVC ABI, because that's what you should do on Windows, because it's like not using Xcode. It's not using Clang to build binaries for macOS. You could, but why would you? Just use the native toolchain, okay? Make me happy. But if you don't want to, if you want to make me sad, there's a GNU ABI thing, which then doesn't correspond really to glibc. In this case, like it means you're using MinGW or MinGW-W64, which also supports 32-bit and 64-bit. And so we have those Windows-GNU targets, which honestly is never what you want unless you know already and then don't listen to me. But then also, usually the Windows targets are like x86_64-PC-Windows-GNU or MSVC. But actually in the target list for Rusty, I find UWP, which is Universal Windows Platform, which doesn't have all the traditional Win32 stuff, all the calls to like open files, start processes, wait on objects and everything, none of that. Now everything is through WinRT, the new system. I don't know what's the current status of UWP, to be completely honest, but we have a target for that. There's a specific target for Windows 7 as well, which I believe was dropped from the rest, but there's still a target for it. I don't know if it works. No idea. Didn't even try. Let's now talk about the way ARM naming conventions work, which is they don't. We have already seen AARch64. We have Apple Darwin. That's, again, all the Apple Silicon processors. We have AARch64 Unknown Linux GNU, which you would get if you install Asahi Linux, for example, on your M1 MacBook or something. But also some laptops that are made specifically to run Linux on ARM64, like the Pinebook Pro, the HP EliteBook, and everything. We have AARch64 PC Windows MSVC because Microsoft's also been trying to introduce ARM64 laptops. The Surface Pro X is an ARM64 machine. They introduced support in like Windows 10 and they improved it in Windows 11 because it lacked x86 64-bit emulation. So there was this weird moment where you could have ARM64 and it could emulate 32-bit x86, but not 64-bit x86. Yeah, because it's all emulation now. But if we look at ARM outside of desktop and laptop computers, then let's count with me, all right? So ARM just means ARM version 6, and then you have ARM v7, which means ARM version 7, and then you have AR64, which means ARM version 8. Of course, James, disagree.
Well, there's even more.
Of course there is.
Even supported in Rust, there's ARM v5 TE, there's ARM v4. If you want to run on like a Nintendo 3DS or something, is still using ARM v4 or something.
Yeah.
Oh, we'll get there. Okay,
we'll
cool.
get there. Don't worry.
Because we're starting to get into I get into a lot of this with embedded stuff.
This is not the singular ARM slide.
Sure.
There's also ARM v7A, ARM v7R, because there's different profiles. I don't know what those mean.
Okay. So real quick.
Yeah.
ARM has 3 major classes of processors now. They've got application processors, which are A. Those are all of your mobile phones, your desktops, and things like that.
Sure.
There's Cortex-R, which are the real-time processors, which are used in vehicles and real-time systems. And then you have the microcontroller profile, which is what, whenever I'm talking about developing for USB devices and whatever, I'm talking about the M profile. So ARM has 3 profiles, A, R, and M.
Wow.
And they are specified in the ARM reference manual, ARM.
Mind blown.
And the compact architecture used, so when you want to use 16-bit instructions instead of 32 or 64 on these target, is thumb. That's the tiny version of ARM.
That's my next slide. That's thumb mode. Yeah. James, I made this slide deck for you.
I've had to go look up the ARM before.
Yeah. So thumb mode, I discovered, I thought it was what the frick is that? Is it the different class of devices? No, it's just a mode. So you can switch between thumb mode and regular mode, right?
Well,
or just the startup?
A-class profiles can do either.
Right.
So before ARM v8, you could switch. They actually had an instruction that would switch the CPU from interpreting large ARM instructions to small thumb instructions. So you could swap back and forth on a Cortex-A if you wanted compact instruction encoding. That's actually the feature of the Cortex-M devices, though, is they only support thumb instructions. They cannot support ARM instructions. So you could run the same instructions on your mobile phone and your microcontroller as long as you only use the thumb subset, which are the sort of compressed instruction mode.
Yeah, the ARM mode instructions are 32 bits, and in thumb mode, there's 16 bits. So the whole program ends up...
Except for when they aren't, but
yeah. I assume there's prefixed instructions as well.
Yeah, there are more. RISC instruction sets are not very RISC anymore.
Yeah. So in terms of how they show up, I'm showing just the arch prefix of the relevant targets. We have thumb v6m, thumb v7m, thumb v7em. I don't know what the E is doing there.
So V6 is Cortex M0, Cortex M0 Plus. V7 is Cortex M3. Cortex V7em is Cortex M4, M7, and thumb V8M are all the 2 digits like Cortex 20-something, Cortex 30-something processors.
That's the first time I've seen a period in any of these.
They got weird with the naming on this of
thumb V8M dot base.
It broke all of our tooling when they did that, both in Rust and in the embedded Rust world. There was a couple of weeks where we just had to rewrite all of the
it's not technically forbidden. There's no rules for target triples. They're not triples. They're not targets. Of course you can put dots in there. Who cares? But there was an understanding before that all of them were A to Z and 0 to 9 and that's it.
With dashes, yeah.
Yeah. Speaking of saving memory, there's a very interesting target, ARM64_32 -Apple-WatchOS. And I learned about this one. It's ARM64 but 32-bit pointers. And it's used for the Apple Watch because they have lots of code in some applications. 64-bit pointers actually use up a bunch of memory just to hold the address of other things. And there's not that much memory on the Apple Watch anyway. But you still want ARM64 because, I guess that's what you're manufacturing. And also you get more efficient instructions for, SIMD and stuff because you do signal processing on there. You do, voice recognition. You do a lot of things. So you get the best of both worlds. You get 32-bit pointers on ARM64.
There's something similar on a Raspberry Pi where they have a 64-bit kernel, but user space is 32-bit, and they've got...
That's my next slide, James. You're so predictable. It's AR64_BE for Big Endian, -unknown, -Linux, -GNU_ILP32. You didn't have a stroke. That is the entire name. I had to shrink the font just so it fits in the slide.
I guess it's still 4 pieces, but
it is
2
4
of the pieces have
There's
bonus
underscores,
data.
yeah. ILP32 is integer long and pointer as 32-bit, and it's the exact same idea, but now instead of being part of the architecture, like ARM64_32, instead of being at the beginning of the triple, it's just at the end with the ABI, like GNU_ILP32. But yes, it's the exact same idea. It just takes too much memory to have 64-bit pointers. We probably don't have more than 4 gigabytes of RAM anyway, so let's just do 32-bit pointers. We are finally getting to the part of the episode that's about Motorola 68000. It used to be used everywhere, pretty much.
It's a very popular retro computing target. Yeah.
The Mega Drive was a 68000. I had a graphing calculator, the TI-89, and some other models of TI calculators were 68000. That's how I first learned about it as a kid. I printed the entire manual of like 68000 assembler just to learn it. It didn't go anywhere. I was too young. I was like 12. I couldn't follow, but I could play Mario on it. That was fun. This has been a long recording. We're almost done. Don't worry. Next up, we have the China slide. There's an architecture called Loong Arch 64. I'm not sure that's how you say it.
It's not long arch?
It's not long. At first I was like, oh, they made Arch64 longer.
Darn it.
It's actually a Chinese word.
Okay.
I don't know if it's Loong, but it's definitely like not just long arch.
It started in 2001 as Godson, and it was renamed in 2010 to Loongson. At first I was like, oh, cool, a new architecture. And then I was like, in March 2023, the United States Department of Commerce added Loongson to the Bureau of Industry and Security's entity list for acquisition of American technology to support the People's Liberation Army. And then you're like, oh, I accidentally opened the Cold War between China and the US. It's pretty much like China being progressively cut off from using American IP. So they had the contingency plan, like, oh, this is actually our own architecture. You cannot prevent us from doing that. It is a spiritual successor to like MIPS and RISC-V that they fully own, so they can just do whatever. In November 2023, they debuted the 3A6000 processor, fabricated using a 14 nanometer or 12 nanometer process. I love when Wikipedia is like, we're not really sure. We didn't send someone to China to check.
A lot of the stuff that I've seen is more focused on RISC-V, because RISC-V also has 64-bit modes, and it seems like there's a lot more interest in around that, but maybe this is more targeted at the classic x86 domain, where RISC-V is like a different take on ARM and things like that.
So the Loongson thing, it was a research project. It was like part of China's policy, made in China 2025. And it was this long plan of like, we're going to stop just manufacturing other people's design. We're going to have our own designs. Like the whole thing is going to be like designed and manufactured and assembled and everything in China. And so that was their thing for processors. Next up, we have seen target triples with 3 components, as triple would suggest, or 4 components.
I'm very interested to see how you pronounce this.
But we also have ones with 2 components.
Especially being in Germany.
You say it. Why should I take the risk, James? It's Fuchsia.
Okay. In American English, I would say Fuchsia.
Fuchsia.
And in German, I'd probably say Fuchsia.
Fuchsia. Sure. Well, I'm going to spell it out. It's F-U-C. This isn't going where you think it is. Fuchsia. It's Google's permanently in a state of research operating system.
It is in deployment. It's in quite a few devices, but
it is in some Google Nest Hub devices, according to my research.
That they've talked about publicly.
Yeah, that's true. They could be running it more internally. And I guess if you're big enough, it's always good to have your own everything, right? Including your own operating system. But yeah, very annoyingly, their targets are only 2 components. They have like AR64-Fuchsia. I'm just going to say it the French way because that's who I am. And x86_64-Fuchsia. I have nothing more to say about this. Next up, we have other arches. When you have 3 components, you're like, which one did they emit? Did they emit the operating system? Did they emit the ABI? So UEFI is the thing that like has replaced the BIOS, I would say. The thing when your computer starts up, it's running in UEFI mode. You can adjust the speed of your fans and everything. You can build for that. You can write Rust code that will run in that mode. There's Redux, which is the kernel written in Rust. There's AR64 Nintendo Switch freestanding, so that's not an ABI. That's the lack of one. It's like you don't have ellipse. You have nothing. Good luck. But it's fun that there's a Nintendo Switch target.
It's basically none. I don't know why they went with freestanding instead of none, but I'm sure they have a good reason.
I don't know. There's another Nintendo one. It's ARMv6K-Nintendo-3DS, and then no ABI. In terms of game consoles, this will ARMv7-Sony-Vita-new-lib EABI-HF. We'll get into what that means right now, actually, because if you look at the ARM targets, so that would be ARMv6, right? You have ARM-unknown-linux-GNU EABI, and then the same thing, but EABI-HF. And the HF stands for, James?
Hard float.
Hard float. Which means that the one that doesn't have hard float has software emulated floating point. So whenever you use F32, it's actually doing all the multiplications and divisions and everything like in software instead of just using a CPU instruction.
That's true, but the reason why it shows up in the ABI is because those processors have floating point registers. So like you normally have integer registers that your processor uses. You have an additional set of floating point registers on there, which you don't necessarily have to use for floating point, but the ABI changes because when you pass, for example, a float by value in a function call, on a soft float target, you would put that in normal registers. If you had a hard float target, you would put that in there. So if you had a function that took a U32 and an F32, the ABI on the soft float target would be to put those in regular registers.
I see.
On the hard float target, it would be to put the integer in the regular registers and the float in the floating point registers. So that's why it's in the ABI field, because you're right. You have to also do all this software emulated floating point. But the reason that it shows up in the ABI field is because you get basically a whole bonus set of registers available there.
Right. I'm tempted to ask why even have floating point specific registers as opposed to just having general purpose. I'm imagining it's like the simplicity of the design.
Yeah, I don't know. All of the floating point instructions will draw from the floating point registers, and they also have some capabilities of like how normally if you have 32-bit registers and you have a 64-bit value, you put them in two neighboring registers, and floats are the same way for F32 and F64s.
Right.
Why? I don't know. Probably because it's easier on the silicon, but yeah, I don't know.
Yeah. Because like on ARM64, if you reinterpret the bits of a float as an integer, that's a no-op pretty much. It's just a type change from your compiler's perspective.
I think it copies it from the float registers to the integer registers.
Yeah, on those processes, it would have to copy it to a different register.
It's probably lazy, like until you actually do something integery with it, it does nothing. But if you want to do integer ops on it, I think you have to move it from the float. Because the instruction encoding, you only have a couple bits to describe what register you're talking about. So if you had just more registers, you'd have to have more bits to encode which register you're sourcing from.
That makes sense. So that's the hard float part, the HF part of those targets. And then there's also EABI. I was curious what the E stands for. It stands for Embedded ABI. It was the successor of OABI, which has been retro-named Old ABI. Yeah. Surely when they made it, they didn't call it Old ABI. What happened there?
It's been gone for more than a decade, but yeah. This is specified in the AAPCS, which is the ARM Architecture Procedure Call Standard 32.
And my next episode will be going through every page of the AAPCS and recording for 17 hours.
It's a good doc. It's actually on GitHub as a Markdown doc. It's good.
I'm sure it is. Next up is NVPTX64-NVIDIA-CUDA. I don't know if that's still a real target. For a while there, it was something you could build to so that you could run code directly on your graphics card. But the thing is, GPUs don't really look like CPUs. They have assembly, they have instructions, they have pipelines, but they have like way too many registers. They do everything in parallel. It's complicated. I know there's definitely ways to write Rust code for the GPU, but I don't think it's through that target anymore. I might be mistaken. James, you're nodding.
I have no idea. I know that like shader compilation is a thing, and I know some folks like the Rust GPU folks and stuff are working on that, but that's totally out of my wheelhouse.
I don't have the notes here, but the README for a project related to the NVPTX64 target says, we got it working one day, and then 3 days later, they added support for 128 bits wide integers, and that broke the targets. But unfortunately, they did not release a nightly Rust-C version between those 2 dates. So there is actually 0 versions of Rust-C that actually still builds this target. I don't know if that's still accurate, but I thought that was very funny. We have S390X unknown Linux GNU. That's IBM System 390. I know very little about this because it's mainframe, and I've never worked with mainframes, but its computer is the size of a room. Not anymore, I guess. It's just the size of a big, like, where do you put your clothes? A big closet, right?
Yeah.
Yeah, very pricey. Yeah, I ordered a couple as well. And you can run System Z, which is IBM's operating system for mainframes, or you can run Linux on there. And so that's what this target is for. We have the WebAssembly targets. The first one we saw was WASM32 unknown, which has nothing. It has no operating system. It has no ABI. It has nothing. It can compute things, and that's all it can do.
This is our none or freestanding target, basically.
Yeah. So if you want to generate random numbers, you have no random number source. So good luck. If you want to time something, you have no timers. You have nothing. So what you do is, because you're probably calling this from JavaScript, you go back and forth between the JavaScript world and the WebAssembly world, which results in your WebAssembly powered thing probably not being any faster because you're doing all those translations, you're crossing the bridge all the time. And so they made a different thing called WASM32WASI. We have the return of triplets with only 2 components. And that one is also versioned. I did not include all the other ones because I predicted we would be tired by this point. But there's preview 1, preview 2. There's so many different things happening. But they're adding APIs for file I/O, network I/O, timers, random number generation, all you would expect from like a kernel. They're adding syscalls essentially to WebAssembly so that you can actually do useful things with them. We are nearing the end of the presentation. I want to reassure you. We've seen ARM64_32-Apple-WatchOS. There's a couple other WatchOS targets. There's AR64 Apple WatchOS, which is what I have on my wrist, which you cannot see even if you go to sdr-podcast.com/episodes. There's AR64 Apple WatchOS Sim, which is what you get if you run the WatchOS simulator on an Apple Silicon Mac. And then there's x86_64-Apple-WatchOS-Sim, which is what you get if you run the WatchOS simulator on an Intel Mac, I would imagine. I didn't check, but that's the only thing that makes sense to me. And then we have our final target, which I love very much, which is x86_64-Apple-iOS-MacABI. James, do you have any idea what that is?
I have no idea.
So it's not MacABI. I said it wrong on purpose to be funny. It's MacABI. Does that help a little bit?
I can imagine, but I have no idea why they have like 7 flavors of ABIs that they'd like to play with, just to make programmers sad.
No, it's to run iPad apps on macOS.
Okay.
Remember a while ago when Twitter made a new app, back when it was still called Twitter, and they were like, we have a desktop app now. And it wasn't like a Mac app. It was the iPad app. And that's a technology Apple calls Catalyst. And that's the target for that.
Gotcha.
We're finally done. Thank you for following me on this journey through target triples. We didn't even talk about some of the funny ones. There's QNX in there somewhere. There's AIX. A lot of things happened. It's fascinating to me because it's history. Because you look at them and you're like, oh, that's right. We used to do that. And now we don't. And it's better now. I want AR64 all the things now. I don't,
Every target triple made sense when it was written. The problem is that it's been written over 40 years, which means the things that made sense then no longer make sense.
Because we talked about thumb mode, and it reminded me of the fact that even today, my desktop computer, when it wakes up, is in 16-bit mode, and then it needs to switch to 32-bit mode, and then to 64-bit mode, and then maybe it's awake.
ARM's gone the opposite way. Newer versions of AR64 can't run thumb instructions anymore to simplify the core.
Yeah.
They can only support ARM instructions. So Apple's actually going the opposite way in that they're removing legacy support, because otherwise the cool thing about ARM is it's kind of like the 386, 586, 686 stuff. You can run ARM v4 on v5 or 6 or 7 or 8, and I think v8 is the first one that really broke something in that it just said you can't run thumb instructions anymore.
So that's target triples for you. They're not triples. Don't let them tell you that. This is a good conclusion, right? This is what podcasts are about. All right. Bye, everyone.
This episode is sponsored by CodeCrafters. CodeCrafters is a service for learning programming skills by doing. CodeCrafters offers a curated list of exercises for learning programming languages like Rust or learning skills like building an interpreter. Instead of just following a tutorial, you can instead clone a repo that contains all of the boilerplate already and make progress by running tests and pushing commits that are checked by the server, allowing you to move on to the next step. If you enjoy learning by doing, sign up today using the link at sdr-podcast.com/codecrafters or use the link in the show notes to start your free trial. If you decide to upgrade, you'll get a discount and a portion of the sale will support this podcast. That's sdr-podcast.com/codecrafters. Thanks to CodeCrafters for sponsoring this episode.